Okay, another topic in which I am not an expert, but this is such an important topic that I read them and then I briefly summarize for you. There are two papers that appeared in Science very recently, and both are focused on extracting lithium. Uh, we'll read a little bit about what the process is, but there are naturally occurring brines, salt solutions, especially in dry regions, semi-arid regions where water is a problem. So anything that involves polluting water or using water for extracting these critical minerals is an issue that you have to address. Plus, you have to address the demand, because as we keep decarbonizing the system, we want more and more batteries, and lithium batteries are now everywhere. So this is about lithium extraction, the brine of the times. New processes directly extract lithium from dilute sources. So this paper summarizes the two papers. Both are very technically detailed and technically complicated, which obviously I'm going to skip and just give you a very brief introduction so that you also know what's happening, like me, or you are an expert and you will follow up on your own. The accelerating global push to reduce carbon emissions is driving substantial demand for clean energy technologies and the materials on which they depend. Nations are vying for critical minerals such as lithium, cobalt, and rare earth elements to produce electric vehicles, energy storage devices, and other low carbon technology. So decarbonization requires all these things, which means we still have to worry a lot about unintended consequences and intended energy usage, water pollution, environmental pollution, and so on. Tremendous attention focuses on lithium, which is primarily sourced from either hard rock called spodumene or natural brine solutions containing lithium and other salts found in continental deposits, for example. However, mining lithium often involves energy-intensive, laborious processes. On pages 1438 and 1444 of this issue, Lee et al. And Song et al. Respectively report efficient ways to extract lithium from dilute brine. These advantages open up opportunities for sustainable extraction from unexploited brine, dilute brines. So if the concentration is too low, then you really have to worry about energy efficiency. And brines are typically evaporated to extract the salts that are in them, obviously, just like regular table salt. But there is a method that's proposed here where the brines are left in place and then some complicated chemical osmotic pressure processes are used to directly extract. And the key is that you want to reduce energy use and you want to be able to extract them from dilute sources so that as many sources can be exploited as possible, right? So here is the schematic from the news article, or the summary article. Lithium extraction from brine. The traditional approach here on the top pumps underground brine into evaporation ponds, as you see for salts, which can take more than a year to obtain concentrated lithium solution. Direct lithium extraction methods proposed here bypass the long vaporization process by using adsorbents, electrodes, or membranes. You get the idea, right? So brine extraction happens, and then you have precipitation of magnesium, which can happen in a few hours, but evaporation ponds then take 9 to 18 months to produce lithium at sufficient concentration. So then you have carbonation to lithium carbonate in about a day after this long process, and then battery manufacturing happens. But now, after brine extraction, direct lithium extraction can happen in a few hours, and lithium chloride production happens in a few days, which then again can be taken to carbonation to lithium carbonate and battery manufacturing. So you can see you can jump the time process. That means labor cost and whatever else is possible. Optimum efficiency of these processes is raised to be an open issue by this summary article. Let's just read the abstract and a few words from the two papers. The first one, Lee et al. Looks at lithium extraction from brine through a decoupled and membrane-free electrochemical cell design. Okay, that's all I will say, but you'll read some detail here. The sustainability of lithium-based energy storage or conversion system, for example, lithium-ion batteries, can be enhanced by establishing methods of efficient lithium extraction from harsh brines. In this work, we describe a decoupled membrane-free electrochemical cell that cycles lithium ions between iron phosphate electrodes and features cathode, which is the brine, and anode, which is freshwater compartments that are isolated from each other, yet electrochemically connected through a pair of silver halide redox electrodes. Chemistry follow-up if you want. This design is compatible with harsh brines having magnesium-lithium molar ratios of up to 30-58, which means lithium is very dilute, and lithium concentration down to 0.15 millimolar, enabling the production of battery grade, so greater than 99.9% pure lithium carbonate. Energy savings of up to 21.5% were realized by efficiently harvesting the osmotic energy of the brines. Whenever you have a solute and a solvent, osmotic pressure can be used to separate the solvent from the solutes. A pilot scale cell with an electrode surface area of 33.75 square meters was used to realize lithium extraction from Dead Sea brine with a recovery rate of 84%. Essentially, they have also scaled it up and show that this is technology readiness is quite high already, not just a lab experiment. We developed a DCMF cell designed for lithium extraction from inferior brines, so concentration is very low, efficiently utilizing the osmotic potential to decrease the energy consumption of the system. The extraction cost was competitive with that of lithium extraction from conventional resources, and the design was simple and easily upscalable. We expect the inherent process flexibility of our design to stimulate the integration of innovative ideas into broader applications. Okay, so let's just make sure I read what DCMF is, and obviously I already forgot because I read these things and then takes me a while to come back and record them because I'm way behind on recording these things. So did we? Yeah, so DCMF is the decoupled membrane-free cell. Decoupled membrane-free cell. Okay, we said it I think here, but I forgot. Okay. The second paper is on solar transpiration powered lithium extraction and storage. Lithium mining is energy intensive and environmentally costly. This is because lithium ions are typically present in brines as a minor component mixed with physiochemically similar cations that are difficult to separate. So if you have lithium and other things and you want to only extract lithium, that can require a lot of energy. Inspired by nature's ability to selectively extract species in transpiration, we report a solar transpiration powered lithium extraction and storage (STLES) device that can extract and store lithium from brines using natural sunlight. So energy usage is reduced. This is like blue hydrogen. Specifically, the device uses a hierarchically structured solar transpirational evaporator to create a pressure gradient which allows for the extraction of lithium from brines through a membrane and its storage in a vascular storage layer. Long-term experiments, various membrane tests, and different size assessments demonstrate the stability, compatibility, and scalability of STLES. This solar-powered mining technology provides an alternative developing pathway toward the sustainable extraction of critical resources. So this is not tested all the way to the end. And again, jumping all the technical details to give you just a briefest of introductions. What are their conclusions? This work reports the design and demonstration of a STLES device that extracts lithium from brines at ambient conditions by using natural sunlight, requiring no arable land and generating near zero greenhouse gases. So it skips the extraction and evaporation ponds and so on. So STLES again is a solar transpiration powered lithium extraction and storage. Solar transpiration powered lithium extraction and storage. Okay. STLES represents several advantages over current and emerging lithium extraction approaches. First, once installed, its passive fashion allows for cost, energy, and carbon effective lithium mining. Second, it can be seamlessly integrated with existing evaporation ponds, which are used in 87% of lithium mining facilities, lowering installed costs. Third, it can float on brines, reducing land footprints. Finally, it's expected that the use of a high transpiration pressure evaporator, so the hydrogel membrane that they talk about in the paper in STLES, maybe they want to call it styles, would facilitate the treatment of hypersaline brines with osmotic pressures up to 400 bar, five-fold greater than the pressure limit of the current membrane filtration systems. So they are able to use higher osmotic pressures to focus on lithium ion as opposed to other ions that are also coexisting. Plus, you remember there are a lot of technologies like sodium ion batteries coming along, solid states instead of a liquid electrolyte that has does the recharging of the batteries after the charged anode is discharged when you use it for something, and so on and so forth. So this is new technology for extracting lithium. It's important for decarbonization, which is our goal in climate change, sustainability, adaptation, etc. So I include these things even though they are technically far from my core expertise area. Some people complain about me going in so many directions, but I think they are important, and even though I'm not providing technical details, I provide enough of an introduction for you to just be aware of what's going on and how hard we are working for solutions. So it gives me more optimistic visions for the future. Okay, I think that's important to avoid climate anxiety and just feeling like you cannot do anything, right? Agency and optimism. Okay, see you in the next topic.